All right, here we have 9.7 probability. So there's a couple definitions that we need to go over. So anything happening for which there's a result is an experiment. The possible results of an experiment are outcomes, and the set of all outcomes is called the sample space. All right, example number 1 is find the sample space. Remember, the sample space is all the outcomes. So for the first one, you toss one coin, and we have two different outcomes. It could be either tails or heads. For the second one, you toss two coins. So you could have either both heads, both tails, tails first, then heads, or the other way around. So we have 4 outcomes there. Alright, so for C, it says you toss 3 coins. So maybe I want to do a chart to make sure I don't miss any. So there's my first toss. Okay, then I have my second toss. And then after that would be my third toss. And each one of your lines here would be an outcome. So I'm going to go ahead and list those. Alright, and then I want to make sure I didn't miss any. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then I'll also want to make sure that there's none that are repeating, and I don't think so. So those are all my sample spaces. Alright, so next we have probability of an event. So the probability of an event E equally likely outcomes and its sample space is then the probability is outcomes over sample space. Alright, so let's go ahead and do an example. Find the probability of A. You toss two coins up. What is the probability that both land heads up? So if we go ahead and take a look at our two coin sample space, that was this sample space. So we have the total for the sample space is 4. And then on the top you put how many times did we get heads up for both? That would only be 1. So your probability would be 1/4. Okay, so the second one, you draw one card at random from a standard deck of cards. What is the probability that it's an ace? So your sample space would be how many total cards you have. That would be 52. And then on the top would be how many aces do we have in a deck of cards. That would be your outcomes. So we have 4. And then you could simplify that and you would get 13. So 1/13th would be your chance of you getting a ace. You toss, so example number 3 is you toss 2 6-sided dice. What is the probability that the total of the 2 dice is 7? So this goes back to the problem that we did in the last section. How many ways are there to get 7 with a 6-sided dice? So we could get 1 and 6, we could get 3 and 4, and we could get 2, and 5. And that's it. But we could also get 5 and 2, 4 and 3, and 6 and 1. So first dice and second dice. So there are a total of 6 ways. Alright, and then for the sample space, we got to decide how many ways are there to just toss 2 dice in general. So we could think about the counting principle and how many different options do we have for the first dice? Well, we have 6, and how many different options do we have for the second dice? Well, we have another 6. So that would give you 36. And so this, if I simplify it, would be 1 over 6. Alright, so here we have example number 4. The following figure shows the number of colleges and universities in various regions of the United States in 2010. What is the probability that an institute selected at random is in one of the 3 southern regions? So first we got to find out our sample space, which would be adding up all of the numbers here. So I'm just going to go ahead and add these up in my calculator. So 311 plus 471 plus 682 plus 266 plus 627, 797 plus 294, 438, and finally 604. And if I combine that into my calculator, I get 4,622. So this is my total here. And what I'm trying to find is what is the probability that it's in the 3 southern regions. So I'm going to go ahead and add those up. So we have, in this case, we have 338, and we have 294, and then we have 794. So we're going to add those up. And we're going to get 1,529. So then our probability is going to be 1,529 over 4,622. And when we divide that in the calculator, we get 0.3308. So if we wanted to write that into a percentage, which we don't have to, would be 33%. Alright, example number 5. In Arizona's The Pick game, a player chooses 6 different numbers from 1 to 44. If those 6 numbers match the 6 numbers drawn, the player wins the top prize. What is the probability of winning the top prize when the player buys 1 ticket? So we have to find the sample space first, which is, remember, the total. So how many ways are there to choose 6 digits from 44? That would be 44, choose 6, and you could use your formula here, or you could use your calculator. In this case, I'm going to choose to use my calculator, and I get 7,059,052. Alright, then we got to think about, in this case, how do we win? So how many ways are there to win? Well, you have to match the 6 numbers with the 6 numbers drawn. So there's only one way to win, is by matching those exact 6 numbers. So my answer would be 1 over 7,059,052. And that would be my answer. Alright, mutually exclusive events are 2 events that have no outcome in common. And if you see an upside down U, that means or, and the U going down is an and. So if and B are events in the same sample space, then the probability of A or B is given by probability of A plus probability of B minus the probability of their unions. If they are mutually exclusive, then the probability is just probability of A plus probability of B. And remember, this is OR. All right, example number 6. You draw one card from a standard deck of 52 playing cards. What is the probability that the card is either a heart or a face? So can you have an outcome where they're both a heart and a face? Yes. So you could see here, you have these are hearts and face cards. So in this case, they have outcomes in common, so they are not mutually exclusive. So their outcome is going to be probability of heart or my attempt at a face is going to be probability of heart plus probability of face minus probability of heart and face. All right, so what's the probability of getting a heart? We have in total 13 hearts out of 52 cards. What's the probability of getting a face? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 face cards with a total of 52. And then how many face cards and heart cards do we have? So that would be 3. 1, 2, and 3. Okay, then we'll go ahead and add those all up. We get 22 over 52. And you could write that as a percentage or a decimal. So we get 0.423, and that would be our probability. All right, so next we're going to talk about independent events, and that's when they have no effect on each other. So if two events are independent, then the probability of A and B is going to be probability of A plus probability of B. So example number 8 says, a random number generator selects 3 integers from 1 to 20. What is the probability that all 3 numbers are less than or equal to 5? So probability of less than 5 Okay, so I wrote probability of less than 5, less than 5, less than 5. That's going to be, all of these are independent. Whether you get one that's less than 5, that doesn't mean that the next one is not going to be less than 5 because it's a random generator. So probability of less than 5 times probability of less than 5 times probability of less than 5. All right, so in total, we're going to have 5 numbers that are less than or equal to 5 over 20, which that could be simplified to 1/4. And same thing for the next one. 1/4 times 1/4. We're going to go ahead and multiply that. You get 1 over 64. All right, so example number 10 says, in 2012, approximately 20% of the population of the United States got their news from mobile devices. In a survey, research selected 10 people at random from the population. What is the probability that all 10 got their news from a mobile device? So we have 10 people, probability of, I'm going to say 1, 2, 3, 4, 5, and 6, all the way up to 10. And these are all the people, so the first person, the second person, third, fourth, fifth, etc. So just because the first person gets their news from a mobile device, that doesn't mean that it affects the next person. So in this case, we're going to multiply probability of 1, probability of 2, probability of 3, all the way up to probability of 10. So what's the probability that that first person will get their news from a mobile device? Well, that's 27%, but we want to write that as a decimal. Okay, what's the probability that the next person will get their news from a mobile device? That's also 27%. And that's the same for all of them, right? So in total, I should have 10 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it's 0.27, and there's 10 of those. We could simplify that to 0.27 to the 10th power. And we're going to go ahead and do that on our calculator. So 0.27, raise that to the 10th power, and you're going to get a really, really small number. So you're going to get 0.00002059. So the complement of an event A is the collection of all outcomes in the space that are not in A. So we call A prime the complement. So that little apostrophe is, I call it A prime. And if the probability of A is probability of A, then the probability of the complement is 1 minus probability of A. So here we have a manufacturer has determined that a machine averages 1 faulty unit for every 1,000 it produces. What is the probability that an order of 200 units will have 1 or more faulty units? So to find the probability of at least one faulty unit, you would have to find the probability of exactly 1 faulty unit plus the probability of exactly 2 faulty units, and then keep on going all the way you get up to 200. So you would have to add 200 probabilities. That's going to take way too long. So instead, we're going to find the probability of them being all perfect. Okay, so all 200 are perfect units. So then the probability of them not being all perfect is that there's at least one or more that is faulty. So then the probability of not perfect would be 1 minus probability of all perfect. Okay, so I'm going to go ahead and find these values here. So first we're going to find the probability of all perfect. So the probability of 1 being perfect is, well, there's only 1 in every 1,000 that's faulty. So the probability of them being perfect would be 9,999 over 1,000. Okay, so that's just 1, but then we have 200 of them. So we would have to multiply this 200 times, which would be raising it to the 200th power. So that would be 0.819. Okay, so that's probability of them being all perfect. So we're going to go ahead and plug that in there. 1 minus 0.819, and we get 0.181. This is the probability of them not all being perfect, so this is what we're looking for.